The issue we'll talk about now is that of selectivity in halogenation reactions. And selectivity is a very important concept in organic chemistry because in most industrial processes we want to avoid creating a mixture of compounds because then those mixtures have to be separated to get pure material. And we can do that the crude way by just getting a mixture and separating it, or we can develop a reaction which is selective, which creates only one out of many possible products, and that is a much more elegant and cost-efficient way of doing that. And so we will consider selectivity in most of the reactions we discuss. And we'll start with the first reaction we discussed, and that is chlorination of methane. And so we mentioned that methane can give only one product, chloromethane, if it's exposed to only 1 mole of chlorine. And the same applies to ethane. Even though it has 2 carbon atoms, they're both symmetrical. So the only product ethane can give is chloroethane. But now if we move to the next higher alkane, and that is propane, we can get 2 different products. One of them could be 1-chloropropane, which is formed by the replacement of primary hydrogen, or alternatively we can form the 2-chloropropane, which is formed by the replacement of the secondary hydrogen. And once this experiment is actually done, we notice that there is a 60% yield of 2-chloropropane and just 40% yield of 1-chloropropane. And so it seems like the propane is simply more reactive in the 2 position than in the 1 position. Turns out that these numbers need to be analyzed a little bit more carefully, because if we look at propane molecule, what we notice is that there are 6 primary hydrogens and just 2 secondary hydrogens. And so to get to these numbers per hydrogen, then the probability of reaction of primary hydrogen would be 40 over 6, which is 6.67% per hydrogen probability for primary hydrogens. Or for the secondary hydrogens, we would need to divide 60 by 2 and get 30% probability per hydrogen for secondary hydrogens. Okay? And so it seems that, simply put, primary hydrogens are less reactive than secondary hydrogens. Where does that reaction difference show? Is in propagation step. Initiation step in the radical halogenation is just splitting of chlorine molecules. So since alkane is not even featured in this step, it's unreasonable to expect that this difference will show up there. But in our first propagation step, we start with chlorine radical and propane, and we can get HCl plus our primary radical, or HCl and the secondary radical. And this would be the primary radical, and this would be the secondary. And so it appears that this thing is simply more stable than the primary radical. And the question is, so since it's more stable, more of it is formed, and then more of it funnels into the final product in the second propagation step. But the question is, well, why would this be more stable than the primary radical? And to answer this question, we really need to look at the orbital picture of radicals to analyze radical stability. And so this is how methyl radical looks like. The central carbon is an sp2 hybridized system because there are 3 hydrogens bound to it, while the radical unpaired electron lies in a p orbital, which is thus unstabilized because of the unpaired electron. This is the orbital picture of the methyl radical. But now if we move to the next higher radical, and that would be ethyl radical, the radical center itself has a very similar structure. But now in its neighborhood is an sp3 hybridized carbon, which has 3 CH bonds, just like any other CH3 group. And this sp3 hybridized carbon in ethyl radical is able to share some electron density with its unpaired orbital of the radical. And this sharing of electron density stabilizes the ethyl radical versus the methyl radical, and it's called hyperconjugation. So this is a stabilization of an empty or half-full radical orbital through interaction with filled orbitals, because these orbitals already have electrons within CH bonds in its neighborhood. Okay? And now if you look at our system, which is the isopropyl radical, things are becoming even more stable, since we now have 2 interacting neighbors. Here we have these 3, and on this carbon we also have 3 sp3 orbitals. And so this would be our isopropyl radical picture. Okay? And of course now if we add one more, then the t-butyl group is the most stable radical. And so the picture of radical stability now is complete. And we can see that the tertiary radicals, the ones that we have carbon attached to 3 different carbon groups, are the most stable ones. Then the secondary radicals are the second most stable. And then primary radicals follow. And finally the methyl radical is the least stable. Okay? So this would be tertiary, secondary, primary, and methyl. Now, how would we measure this? Is this a measurable quantity? And the answer is really yes, because if these radicals if the tertiary radical, for example, is easy to form, then it means that the energy involved in its formation will be lower, because we need to input less energy to form something that is stable. And that is, of course, measured by bond dissociation energies. So if you look at the CH3H bond dissociation, this value is 104 kilocalories per mole. If you look at our primary propane dissociation energy, we get a primary radical in each radical. This is 95 kilocalories per mole. If we keep going, and now we take the propane again, but instead we get a secondary radical, this value will, as expected, be lower. This value will be lower at 95 kilocalories per mole than this value, which I mistakenly written as 95. It's actually 98. So this will be more favorable, since the resulting radical is the most stable one. And finally, when we take the butyl radical formation, in H, we'll get 91 kilocalories. So it seems like it all fits in. Okay? And so now we can really see our explanation for the halogenation effects. Basically, as we start with propane and chlorine, we go through the same starting material, which is basically just propane plus Cl dot. But then on the bottom here we have our secondary radical and HCl, and here we have a primary radical and HCl. And this difference is a difference in our radical stability, and so this is exactly the 3 kilocalories per mole that come out of this state. And there's also a small difference in energy of activation. And this is important not for thermodynamic purposes reason, but for kinetic reasons, because the small difference in energy of activation means that not only getting more stable product at the end, but we also more stable product is formed faster. Okay? And so this sort of explains why the selectivity when it comes to an alkane. But what about different halogens? What about bromine? How does bromination work? What are our effects in bromination? And so if we look at our reaction with propane and bromine, and we expose this to light, but now we also need to heat this to 150 degrees because bromine is less reactive. Then we'll get our primary bromide, and as expected, the secondary bromide. And the yield at 3% here and 97% here. So now the difference is much more dramatic, because if we divide this by 6, we'll get 0.5% per hydrogen probability, whereas here the probability is 48.5% per hydrogen. So much higher. Okay? And this whole thing means that bromine is more selective than chlorine. Okay? And now, well, the question is, well, this might seem like a little contradictory, because chlorine is more reactive, yet bromine is more selective. And then that really is one of the paradigms in organic chemistry, that reactivity-selectivity balance. That more reactive things, they are more reactive with everything. Whereas and so therefore they do not exhibit much selectivity. Whereas less reactive things will react only with things that are very favorable, but those that are not so favorable will just be under the background level, and the reaction will not occur. And so if you look at the energetics of bromine interaction with an alkane, here it is. This is our propane reacting with bromine. In our first step, we can get the primary radical, that's HBr, or we can get our secondary radical, plus HBr. In this case, the bond bond dissociation energy of the propane hydrogen bond is plus 98 kilocalories per mole, and the formation of hydrogen bromide bond is minus 88, which means that they're still plus 10 kilocalories short. In this case, it's plus 95 and minus 88, and so we're plus 7 kilocalories short. Okay? And so now this difference is just 3 kilocalories per mole, and you will notice that it's the same difference that we observed in the chlorine case. And so if we plot our chlorine case here, then we will get this sort of difference of 3 kilocalories per mole, but the reaction is exothermic, and so this is chlorination. But if we do it on bromine, then this difference will be again 3 kilocalories per mole, but the reaction will somehow be much more selective. And the reason for this selectivity lies in the difference in activation energies. In case of chlorine, this difference is relatively small. In case of bromine, this difference is relatively large. Okay? And this difference tells us why the more stable product is formed much faster in the case of bromination and in case of chlorination, but both products are formed relatively fast. It's just that we get more unstable. And so this graph really explains the selectivity that we observe in bromination, and this is a so-called Hammond postulate, which will be the topic of our next series of slides.